I'm going to turn it over to the team and let them introduce the Jetson 2.0.
All right, so hello, we are the Jetson 2.0. Our team is Mateo Cannibal, Arvin Draffin, I, Idris Moran, and Hunter Robinson. So the goal of our project was we took a look at the existing Jetson cluster that exists in the engineering building, and while it performs its task pretty well, it does what it needs to. We were looking for an upgrade, especially because we had a few different things in mind. Since the student body is growing rapidly, we wanted to provide a cluster that could both perform better and as well have more scalability. And in addition, we wanted to give it some good looking features. So we have marketing from our marketing requirements. We were able to derive engineering requirements. We got most of the things done, although you could see the requirements highlighted in red were scrapped entirely due to COVID-19, and the one that's highlighted in yellow was able to get done. It was affected, but we were able to get it done. So the things we were able to get done were that we have a public-facing statistics view that shows utilization statistics, memory, etc. It consists of both real-time data as well as historical data, so you can go back and look at how it has been operating as well as how it is doing now. And it can handle projects that are done in classes, for example, in the parallel programming class taught by Dr. Wells, CPE 412. It can execute projects in parallel. And like I said before, one of the primary goals we had was scalability. So not only having something that's more powerful now, but that can be upgraded, let's say 5 years down the line or so. So the things we wanted to have were power management features, which are necessary, but due to COVID-19, we had to scrap that. And the initial goal of our project was actually to develop 2 clusters and build both and compare them and see which one performed better. And in addition, we wanted to have GPU, but that was more of a luxury anyways, or GPU performance wasn't a luxury, but it was something we weren't completely sure about, and with COVID-19, we were not able to get it done. So the engineering requirements, we designed our own PCB. It was slightly impacted, but not a whole lot. We have a .NET Core MVC web display. It displays the utilization statistics, and the database stores data from the past week historically. And by doing this, we use a data agent that collects data from each node and stores it. And to perform in parallel, we configured Slurm, MPI, pthreads, OpenMP, and we're hoping to also do CUDA on the cluster. And again, we were not able to build 2 clusters and compare them. And we have a data collection agent that reports data from each node. So our initial considerations, we thought to create one from existing parts. However, what we were looking for was pretty hard to find, as well as for the PCB design, we ended up going with a custom design rather than buying something pre-built because A, size, and B, also just functionality of what we wanted it to do. And again, our goal was to get look at 6 clusters, and from those, just from a perspective of cost versus performance, narrow it down to 2 and build 2, compare them. Obviously, we didn't build 2 and compare them, but one of the 2 key things were cost and performance. It wasn't just about how much bang for your buck could you get, but also meeting a minimum requirement for performance and as well as scalability, and then as well as considering the cost like as a maximum thing. So these are the 4 that we did not go with. The Jetson AGX and the Jetson TX2 are really nice. They do really great stuff, but in the end, they are either too expensive or they draw too much power. And so some of the more feasible options were the Pi series, the Raspberry Pi 3 and the Raspberry Pi 4B. The 3, while it was great value, it wasn't powerful enough. And the 4B, it did have a lot of good things going for it, but it didn't have, or the GPU performance was not as good as we wanted it. And so the 2 that we ended up going with were the Jetson Nano and the Jetson Nano and the Odroid N2. They both had their pros and cons, which is what we wanted to compare. The Jetson Nano has the GPU advantage, but it has a slower or an older CPU, whereas the Odroid has a slower GPU but a much better performing CPU. And another thing to consider was the storage. Jetson Nano uses micro SD, which isn't as favorable, whereas the Odroid has faster storage with using eMMC.
Okay, due to issues with the current clusters running on campus, with some of them locking up, it was decided that a management solution for dealing with power control to hard reset these devices were needed. Initially, we wanted to go with a system that was more consumer oriented, that could come from Adafruit, for example, who builds a I2C module and the INA module shown at the bottom. But due to size constraints, because that system would be significantly larger than a PCB, that was scrapped. Originally, we wanted to go with mechanical relays due to their being cheaper and not having to do some kind of switching design, but it was decided that solid state would be a better idea to not go with the issues that a mechanical relay has. So there's two parts to this system. There's a STM Nucleo F7 46ZG microcontroller. It is an ARM microcontroller. It allows us to control the power status of each Jetson module and receive power statistics from an INA 219. The power management module is a custom designed PCB from Osh Park. It allows us to control up to 3 amps, 12 volts from each Jetson individually. And as said, it supports up to 5 devices. Okay, the design of the PCB, it's a 2-layer board with 2-ounce copper. Anything less than 2 ounce would have made the board absolutely huge, or it would not have worked with some of our parts. And that the cost of going to multi-layer would have been significantly more than the 2 ounce. We have filter capacitors on each output for each Jetson module. And we have opto isolators to protect the GPIO pins that control the switching to each of these modules from a drain to gate short of the MOSFET in the case that it fails in that way. This is just a schematic of the base system for the power management board. Go to the next slide. Okay, the STM32 microcontroller receives all of our statistics over I2C from these INA 219 sensors. We wrote this in C# using Nano Framework, which was just used to make this a lot simpler to speed up development time. We were originally going to go with Intelligent Platform Management Interface, called IPMI. This is used in virtually every server that exists. So we wanted to integrate it into the UH system in a way that it wouldn't be special, so it would be very easy to use, but this was cut due to COVID because it'd be impossible to bug check something as complex as that. Okay, because of COVID, we did need to do something to get our website running and to try to work on Slurm without the devices, without the Jetsons and the Odroids. So it was decided to make a virtual cluster to help us along with that. It runs on Windows Server, they're Hyper-V. We have a gateway that hides our 3 identical nodes set up with the exact same CPU memory allotments, which is 4 cores, 4 gigs of RAM, so that this would better match the systems that we have in real life.
So the next phase of our project involved the web interface, which was used to display utilization statistics gathered from the cluster itself. And this was done in part by Mateo, who wrote the data agent, and myself, who wrote the web client. And we collaborated by sharing Jetson models, which you can see here. This is a collection of submodules that is used to basically provide a common interface between providing data to the database and then retrieving it from the database. So to do this, we took advantage of Entity Framework Core, which provides a method to kind of abstract away from the SQL So we can do all of our coding in C# while not having to deal with the low-level SQL commands and that sort of thing. So it consists of 3 subcategories: communication, context, and database. The communication database or portion was not used as part of our project. It was added sort of later as a port of something Mateo had written. But by that point, since it was separate, we decided to leave it unused, but for a future group, they would be able to benefit from that. Next slide, please. So the database portion of Jetson models consists of the classes by which data is sent into and retrieved from the database. So example of classes in the category are cluster, node, node utilization, CPU core, and node power. So basically we took the cluster from a top level perspective and we broke it down into smaller and smaller chunks. So we were like, okay, we have a cluster, and the cluster is made up of nodes, so we need to report data for each node. Looking at the node itself, we decided to divide reportable data into utilization data and power data. Utilization data consists of stuff such as memory utilization, memory availability, and CPU usage, while node power consists of data reported such as voltage, current, and power usage. The power data would be in part reported by the power management module discussed by Hunter in the previous section, while node utilization data would be gathered directly from the cluster itself. Next slide, please. And the context set of classes provides a interface between the database classes and the database itself. So an example of a class within this is the CPU core to string converter class. So one of the decisions we made was to store CPU utilization as a comma-separated value, or comma-separated list of CPU utilization values. So basically, for every node that has n clusters, we would have n percentages from 0 to 100 separated by commas. But in our C# code, this was represented as a list. So in order to do that, we needed to provide a conversion between the CSV string and the C# list. And that class is what's responsible for doing that. And in addition, the cluster context class basically initializes the database and is what is used to interact with the database for pulling data and then storing data. Next slide, please. And this is the overall class diagram for Jetson models. So as you can see at the top, it's kind of a hierarchical structure. It's the highest level entity is the cluster, which consists of properties, obviously, as I said before, nodes, but it also includes the type of cluster, which should be something like a Jetson cluster or a Odroid cluster or a generic cluster, which is definable in the configuration file when the cluster is set up initially. It also includes stuff like the name of the cluster and then the ID of the cluster. And as you can see, the same sort of structure is applied for nodes, and then within each node power and node utilization. Each one contains a timestamp saying when that particular data was received, and that is what's used to pull the latest data as well as historical data for displaying in the web client.
The data collection agent is responsible for collecting utilization data for each slave node and sending it to Jetson service. The utilization data, along with data identifying each node, is contained in an instance of the update message class. The node client contains members that describe the current state of the node. In addition, it contains an update function which updates those members, along with a send data function which JSON serializes an instant of update message and sends it to Jetson service through an HTTP put request. These two methods are periodically executed by timers in the program class. Next slide, please. Here is a class diagram. So as you can see, the node client has an aggregates the update message class and all those other classes as well. Next slide, please. Jetson service is responsible for receiving data sent by the data collection agent and storing it in a database shared with Jetson Web. The node module class functions as an HTTP server which receives put requests routed to /node update. When a request is received, the body is deserialized and sent to the receive message function, which adds it to the database. Next slide, please. And there is the class diagram for Jetson service. Next slide, please.
So the web application, similarly to the data agent and the Jetson models, was also written in C#. This was an initial requirement that we got at the beginning of the semester. Basically, one of the upgrades we wanted to provide to the Jetson cluster was a public-facing utilization statistics display. So the main idea was it should be intuitive, easy to use, but also contain information for people with maybe like little to no knowledge of what the cluster might be doing, and appeal to people who may have a bit more background in parallel computing or high performance computing or that sort of area. So as with Jetson models, this also employs Entity Framework Core as well as .NET Core. So .NET Core is produced by Microsoft and is cross-platform. So we picked that as opposed to potentially some other methods because that would provide or reduce the chances of compatibility issues and that sort of thing into the future, as we would possibly no longer be maintaining it, but we wanted any future groups to be able to not have to deal with any compatibility issues in that regard. And as Idris described earlier, it uses the model view controller design pattern. Basically, as I described earlier, the models hold data that is retrieved from the database. The controllers package that data and send it to the views, which then display the data as basically the web pages that you see. And to host the website itself on the master node, we used Nginx, which is a web server, and it also works hand in hand with Kestrel, which provides the reverse proxying. Next slide, please. This is the entity relationship diagram for the web application. So as I described previously, you can see the three main sections with views at the top, controllers in between, and then models at the bottom. So the cluster itself, as it's supposed to update data as it's pushed, needs to be able to reflect that. So our initial approach very early on was to manually refresh the page, but we soon decided this was pretty clunky. So we replaced this with a Ajax JavaScript function in the cluster utilization real-time pages. And that's represented by the dynamic refresh model down at the bottom and in the and in controllers as well. So once the initial data is populated, the Ajax call queries the database and it receives the data provided by models in the dynamic refresh category to populate the parts of the page that we expect to change. So this includes stuff like memory usage, CPU usage, that sort of thing. But like the cluster ID would not be expected to change. And since we wanted to keep the overhead minimal for that repeated data transfer, we opted to exclude some of those more static categories. Next slide, please.
So by the end of the semester, we were able to get plenty of things working. We got a functioning power management module that's able to control devices, and we were able to verify that. A web interface was designed. We got it to look nice and elegant, and it provides the data we need, both of historical and real-time data. And we have a data collection agent that obtains this utilization data and sends it to the database. So obviously, the completion of the project was impacted by COVID-19, especially the physical parts after mid-March or so. Most notably, the two physical clusters we can do and the IPMI-based power were not able to be completed as a result of the COVID-19. However, most things, the major things that we set out to do, we were able to get done, despite the fact that we had to work remotely. And so the reason why we were able to get all this work done was our project management philosophy. Instead of sticking with a rigid design that or was sticking with a rigid schedule that controlled everything. We had a philosophy that so long as we set due dates, so long as we get dates, and so long as we hold ourselves accountable, we were able to complete things, and we did. This was aided by the fact that we knew each other from previously, so we knew what each other's capabilities were and what we could get done, and we had a better idea of when like a realistic due dates. So in order to communicate with the customers, we used agile development to get, especially due to the changing or the often changing requirements, it was pretty necessary to maintain constant communication. And this is more important, especially during the COVID-19 pandemic, because things had to be adapted on the fly pretty fast. So we needed to have constant communication. And again, despite the fact that not everything got working, due to the modular nature, we were able to test each individual part and to verify that it worked, so that we wouldn't have a bottleneck of waiting for one thing to be finished while everything else is waiting to be tested.
Our team measured progress along the way by establishing checkpoints for the major milestones of the project. Progress is measured by how many checkpoints were met. Discounting the checkpoints which were eliminated after the COVID-19 rescope, the only checkpoint which was not met completely was the virtual machine setup and testing of software checkpoint, which was only due to the fact we cannot get Slurm to function properly. Next slide, please.
Sorry. This is a cost breakdown of all of our systems. As you see on the left is the power management system and all of its quantities, part numbers, and price relative to quantity. Each of these does take into account any volume discounts that occurred with that quantity. Then we have the Odroid cluster and the Jetson Nano cluster. Things that were striked out were because we already had similar things such as a power supply, switches, and Ethernet cables. So those weren't purchased, but were included in these tables just for reference in case anybody needed it. This is a breakdown if we wanted to go full with a different port, different Ethernet cables, and a different power supply to be able to handle the current. The power management module did not make this slide. We simply ran out of time on that, but I can say that it would have been a drop from $133 per board down to, or $133 for 3 of the boards down to something in the realm of $115 for 3 of the boards. Now we have a demonstration of the website running. So if we just click that.
It's not private. Okay.
Yeah, just hit advanced.
Okay. Okay, and
Should scroll down and say, yeah, just proceed.
proceed. Okay.
Okay, that's cool. Yeah, we didn't get a certificate on, so.
Okay, here we go. Okay, so I should know.
Okay, so each one of these on the welcome page, if we had many clusters, you would see many different utilization click buttons, and each one you click and you go into a breakdown. So if you click the NVIDIA Jetson one, and each of these is a picture that you can look at any time. Okay, we're having issues on the back end, so we'll guess we'll ignore that. But what you would see is a memory graph, a CPU graph, and power statistics. Obviously, power statistics would have to be fake at the moment because, well, we don't have the full cluster running. We're trying to fix the issue with the data right now, but we can go to the About page. If you tap top left, there is something in there. I do have a demonstration of the power management module running as that link right there that I can attempt to look at real fast. So you put that. Right now, all of these devices are off. There's no power going to any of them. And when that button's pressed in a second, Okay, so you'll see the light comes on in the microcontroller, and then the 3 Odroids that I currently have connected to the 3.3 volt come on correctly, and that these 2 here are off. So when I go over here and I touch these 2 leads together to the main 3, you'll see the other 2 come on. There we go. That's just to demonstrate that the power control system does function, even though it was not run by the microcontroller.
Okay.
Okay, so we should have the
If
data
you go back
working
to
now.
the home page, right,
And
the
then,
utilization, you can just hit the back button at the top. Right, if you go to home or click Jetson Web and then click on NVIDIA, we should have it working now.
okay.
Right.
Okay, great.
So if you, as you can see, if you scroll down, you can see a bit more with the voltage and current, which is fluctuating a bit more. But you can see the dynamic refreshing occurring here, where the page isn't reloading, but the actual data within the graphs is. The memory usage and node utilization are pretty constant. There's not really anything going on the cluster right now, so the utilization is pretty much 0. If you hover over like any of the graphs, you can see the exact number. So for example, there is a slight bit of usage there, but it's pretty much not anything at the moment now exactly, I guess. There we go. And then if you scroll up, we can go to, oh, I guess we're doing something on the cluster now.
I'm currently running just a quick while loop with a pointer just to prove
Yeah,
that
that
our
would be good.
do update in real time. So that was just there to prove, just there to make the graphs look
Right.
special.
And then if you go up to the, we can go to the advanced view too. So if you scroll up,
Okay.
it's at the right. You can see here's voltage. We figured that wasn't as critical of a statistic to have on the main page, so we left it here as a advanced view. And then there's a table below that where you can see the IP address of the node, the operating system, the uptime, and then the time at which it last received an update. So that way, in case there's a node that isn't properly functioning, which might not be reflected on the utilization graphs, if you see an update received that was maybe 2 or 3 hours old, or even 2 or 3 minutes old, if your update interval shouldn't be that long, then you know you might have a problem. And then you can go look into it. We figured that was something that might not be as important to have on the front page, but might be useful for, I guess, someone if you wanted to click into this view. And then our final view is the historical view. So if you click the button to go back to overview and on the right, or back, that works too.
Okay. Okay.
And then you click on historical in the upper right there. You can see power usage, memory usage, and CPU usage over the past, in this case, hour. So it samples approximately 100 data points over that interval and then plots them. So you can get an idea of exactly how memory usage is going. And then you can see the spike right there when Hunter ran the his program. So CPU usage is below that as well, which should also see a spike. I guess it was only on one node. It reports data for both nodes, but I guess in this case, all the computation was occurring on just one node. So this graph would reflect that. If the other node was there, it would be, I guess, in this case, an orange color. And then if you scroll up to the top, Dr. Wells, if you hover over the past hour, there's you can see the drop down. You can select either past day or past week. So if you want to see longer data time span, you can do that as well. I think you're still on the same one, Dr. Wells.
Okay, this is past day.
Right. That should do it. Right. So if you see on the timestamps at the bottom, it gives you a span of almost exactly a day from the of the clusters running. We've left it running a little while just so data can be populating in the database, so we could have sort of a longitudinal view. And then, yeah, that's pretty much, yeah, there's the week one as well. And that's pretty much it for the web end of things. These pages do not dynamically refresh. We felt that was a lot of data to be pulling, especially at every 1 second intervals. So we have it where every 60 seconds it just refreshes the page. We felt that most of the time users would be spending their time on the main cluster utilization real-time page. So that was where we put most of the dynamic refreshing.
Okay.
That's all we have. So if there's any questions, this would be the time.
I'm trying to see if I'm live. Am I live? Okay, yes, okay, I am. All right, in questions, please.
Okay, on the power management, you showed me transistors. What about the actual controller? Is there anything working on the controller?
I didn't have, okay, because of COVID, we couldn't do any testing. So there's nothing working on the controller end. I have some base firmware written to do I2C reading and configuring of the sensors, GPIO, and some basic user configuration that can be saved to the flash on the board. That's what we have right now, but no IPMI what had a chance to get started, unfortunately.
Okay, on this performance measurement, this system is written with a lot of Microsoft libraries. Are those available for ARM?
Yes, the Nano framework was specially written to convert C# to ARM-based code. So everything on here should be good to go. So if I have the firmware in a GitHub, obviously I haven't tried to run it on the using their Nano installer. I forget exactly the name, but I did make sure that existed for the platform before writing it.
So the web server itself can also run on?
No, the web server runs on the Jetson master. There is some hosting capability that Nano Framework can do, but we decided to put that data on the master because we had to get OS level specific data from each node. And the easiest way to deal with that was to not do a loop around the system and have to go back to the IPMI and have it basically be in band instead of out of band. So it was decided to run the web server on the master node.
Okay. What is the CPU utilization of the process that's doing the monitoring, the performance measurements? Usually when you start getting that much data that quickly, that can get computationally expensive.
That I wouldn't know. That would be Arvind or Matteo, if they have an idea.
Yeah, that'd be Matteo. He wrote all that stuff.
It's very low. I don't know the exact off the top of my head exactly what it is, but I guess you could check, Connor. Yeah.
So I guess I'm a little confused about what we're talking about here. I saw one slide that says you put something together on a Windows hypervisor.
Oh, that's our cluster. That's our virtual cluster because we needed something to be a stand-in for the boards. So I did as much as I could to make sure that these virtual machines matched our real machines so that we could accurately write software for them.
So you simulated ARM on x86?
It's not on ARM, but we do have some experience running .NET on ARM, and there's no issues there. It runs really well nowadays because of Microsoft's involvement in, making it for Linux and the other platforms.
So could you explain the VM part? What you were having some issues, I know, with things like getting Slurm to execute, appropriately, and other stuff. What was the, what has transpired? How does the VM work? What were you able to accomplish there? And exactly what software. I guess be possibly going over it again, but being more specific on that. See if you can just help me, and also some of the issues that you've had.
Yes, the virtual machines were originally created to speed up the process of designing the web server and designing these data agents and configuring Slurm. They were set up in, I want to say, late January, early February, because the two different clusters, their hardware didn't come in until late February, early March. So it was an idea to get those to basically be able to do something, while we were waiting on hardware. And then, of course, doing all the configuration and all of this stuff on a virtual machine helps us figure out exactly what we need to do on real hardware, so that when we go to real hardware, we have a cleaner idea instead of basically putting a mess everywhere. Some of the issues we had, obviously, Slurm didn't get running quite correctly. It's there. It does communicate between all of the nodes. I've got an MPI to run, but I have an issue of where Slurm appears to, instead of just running a single process, it takes the processor count that you give it and it runs it X amount of times with MPI running. So you end up getting 8 MPI runs of 8 processes, which is obviously not exactly what we're looking for here. Does that answer your question?
I don't know. I just partially so one of the issues with that was sort of a showstopper from the on the real hardware, performance wise and otherwise. I guess that you're saying in terms of each core got assigned to all 8 processes. One core got assigned that on one of your virtual machine elements. It wasn't working. It wasn't scheduling among your overall virtual cluster. Is that what happened with Slurm? I mean, all the MPIs, are all on one, right?
Yeah. If you look at like how we have it now, where you say, I want 8 processes, and that runs on the master node of the current Jetson cluster. So if I put in 8 processes to Slurm, it will make 8 processes of our file, and it has MPI in that. It doesn't. If I don't run MPI run as part of the Slurm command srun, it doesn't communicate MPI properly, and it'll just run 8 processes on those 2 nodes. So you'll see an even split: 4 processes run on slave 1, 4 processes run on slave 2. If I run MPI run, we get that same result of 4 and 4, but we end up actually communicating across the nodes properly. So you'll see the report coming from slave 1 and slave 2, but we run it 8 times.
All right. Okay. So this is just inter-process communication doesn't work right with just the Slurm command.
Yes, something seems to be off. I've read quite a few different universities that run Slurm. They don't appear to have this issue with MPI. It should just work. So I don't know if that's an issue with our program, perhaps, or not. But it was compiled with MPI run or MPI C++ and everything. So I'm not quite sure why this issue exists. But we did get it to the point of where they communicated at least properly somewhat.
Okay. Did you have some benchmarks that you ran from, MPI, from taken from the class for those of you who took it, or something like that to test it out? How did you, or was it just a, some sort of a program just to verify the communication, was correct?
Yes, I ran, it was the Hello World program, and I modified it to print the host name of each of the running node so that I could properly tell how it was communicating. So I can confirm that it does communicate properly.
Okay, but what about sending a message from one memory space to the other? Is it when they're on different virtual machines? Does it do that okay? Like a MPI send, MPI receive, that combination?
Yeah, it does appear to do that properly. I wish I put the screenshot in here now, but you'll see.
You want me to stop sharing?
It'll say who the master node is, and then it'll say, this response came from this node, and this response came from that node.
All right. Did you want to share screen? You want me to stop sharing so you can, or do you?
Yes, let me clear my screen off here and log into the cluster.
Okay. And then while you're doing that, somebody else can ask a question. So it could be from another team member, so you don't have contention.
And just a comment on the commercially available. I can think of two different commercially available solutions off the top of my head. The hard kernel people actually sell. I think they call it an HC1, a home cloud, which is like an XU4 with a lot of the peripherals missing. So it's just a network interface for the most part. And there's another solution, I don't remember the name of the company, but it's basically a bunch of rack mount Raspberry Pis, or it's a rack mount enclosure that's a tray full of Raspberry Pis that was used by Lawrence Livermore National Labs. And that actually came out sometime after our original Jetson cluster. So there are some solutions out there that do this, and of course you're not going to see any Bitcoin mining on this anymore. But at one time, some of the ARM platforms early on were popular for Bitcoin mining, and there were some solutions sold that way as well. So a lot of the hardware is the same. You just use it in a different way. Communications would be a little more important for HPC than for Bitcoin mining, but there is some stuff out there.
Thank you. That sounds good. Very, very useful information. If it's not easily obtainable, that's okay. If you.
Yeah, it's an issue with broadcasting at the moment. Yeah, but I'd have to see how it's broadcasting. Because to run this one, you have to broadcast the file every time, and I don't remember the command off the top of my head, and Slave 2 doesn't appear to be broadcasting that. But yes, MPI communicated across nodes properly. There was just an issue with how Slurm was dealing with sending out the actual files, and it was just running them too many times. It really only needed to run it once. That was the issue.
Okay.
Yeah, there tend to be configuration issues with all of these queuing, or not issues, but gotchas with all of these queuing systems. So to properly configure separate cores versus separate nodes, and not the old school stuff that we used to use didn't really handle it, and we've got the existing Jetson cluster configured in a particular way to be ignorant of cores, so that Dr. Wells can do some specific things for 412. But there's a fair amount to the configuration with any queuing system for HPC.
Yeah, I assume maybe I had missed something along the lines with how to deal with processing and physical core count, but I just could not find it in time. I was dealing with other things.
Okay. All right. Well, any other questions? Okay. Well, thank you. Thanks everybody for attending, and this is the last one. This is actually the next to last total one. I have one more. We have the class has one more tomorrow, and but anyway, thank you very much. It was so I think this is I've learned a lot in this the Zoom era, so to speak. And that I think some of this is transportable to if we ever go back into the normality again. But anyway, thank you again. Thank you, team. And that's all.
All right. Thank you.
All right. Thank you.
Where's the